Welcome back to the deep dive. Today we are not just analyzing a topic, we are stepping into a simulation.
A very particular kind of simulation.
It is. We have a stack of sources here, Sagan, Hawking, Green, Tyson, and they all seem to enjoy, terrifying us with the fragility of our existence.
It's the best kind of terror, though, the kind that comes with a heavy dose of awe and maybe a side of calculus.
Exactly. So I want to set the stage immediately. We're borrowing a concept from Carl Sagan today. He proposed this device, a mental construct called the magic gravity machine.
A classic tool for thought experiments.
Yeah.
The idea is that you have this, like a dial where you can control the fundamental constants of nature.
Yeah.
You can turn gravity up to 1 billion Gs. You can turn the speed of light down to a crawl. It lets us, break physics just to see how the pieces fit together.
And today we have a very specific mission. We're taking that magic gravity machine, we are pointing it directly at the center of our solar system, and we are turning the gravity dial for the sun all the way down to 0.
And just to be super clear, we aren't blowing the sun up. This is not a supernova scenario.
No, not at all. In this scenario, the sun simply vanishes, deleted from reality. One moment, it's there, this massive ball of plasma holding us all together, and the next moment, we'll call it time 0, it is just gone.
And the question is, what happens next? And I don't mean next week or next year. I mean in the immediate seconds, right after that deletion.
Because this isn't just a disaster movie setup. As I was reading through the material, specifically Brian Greene and Hawking, I realized this scenario is actually, it's a battleground. It is a specific scenario you need to pit Isaac Newton against Albert Einstein.
It's the ultimate heavyweight title fight of physics. The disappearing sun problem forces us to confront the speed of light, the nature of information, and really the very fabric of space-time.
So let's unpack this. We're going to walk through this timeline second by second. Let's start at time 0. The sun has just vanished. I'm sitting on a beach in California. You're maybe hiking in the Andes. What happens?
Nothing.
Absolutely nothing.
Absolutely nothing. At time 0, the sun is physically gone, the mass is deleted, but you, on that beach, you're still watching the sunset. You're feeling the warmth on your skin.
The plants are still photosynthesizing.
They are. The tides are still being pulled. Life just continues perfectly normally.
That is such a psychological disconnect. We are technically orbiting a ghost.
We are. And this comes down to the yardstick of the universe. As Sagan pointed out so beautifully, the cosmos is so vast that our human measurements, miles, kilometers, they're essentially useless. They're just too small.
We have to measure distance in time.
Exactly. We talk about light years, but here we are talking about light minutes.
Right.
Precisely. Light travels at a finite speed. It's incredibly fast, 186,000 miles per second, or roughly 300,000 kilometers per second.
That feels instantaneous to us.
To give you a sense of scale, in the time it takes your heart to beat once, a photon of light could circle the Earth about 7 times. So in our daily lives, it is instantaneous. If I turn on a lamp across the room, you see it instantly. But that's only because the room is small. The solar system is not small. The sun is 93 million miles away.
And doing the math, that distance divided by the speed of light gives us
8 minutes and roughly 20 seconds. That's the transit time. That's the commute for light.
So when we look at the sun, we are never, ever seeing it now.
We never see anything now. That's a fundamental truth that Hawking really drills into. Even when you look at a friend sitting across the table, you aren't seeing them in the present. You're seeing them a nanosecond in the past.
Because the light had to travel from their face to my eye, it takes time.
Exactly. It's a tiny, imperceptible delay.
Rare.
But when you scale that up to the sun, the delay becomes 8 minutes. If you look at Alpha Centauri, our nearest star, it's 4 years.
4 years.
You're seeing it as it was 4 years ago. And if you look at the Andromeda Galaxy, you're looking 2.5 million years into the past.
It's like archaeology, but with light.
Astronomy is archaeology. We're just digging through layers of time. So back to our disappearing sun. At time 0, the source of the light is gone. But the river of photons, that steady stream that left the sun 1 minute ago, 2 minutes ago, 7 minutes ago, it's still crossing the void.
It's like a hose. You turn up the spigot at the house, but the water that's already in the hose still has to spray out the end before it stops.
That is a perfect analogy. We are getting wet from water that has already been cut off at the source. We are basking in sunlight that no longer has a sun.
Hawking introduces a concept here that I found really helpful for visualizing this. He calls it the future light cone.
Yes. This is crucial for understanding causality. Imagine an event happens at a specific point in space and time, our sun vanishing. That event isn't just a dot. It radiates influence outward. It expands like a bubble, moving at the speed of light.
So everything inside that bubble, inside the cone, knows the sun is gone.
Right. If you are inside the light cone, you are causally connected, you are affected, you have the information. But Earth, for those first 8 minutes, we are geometrically outside the future light cone of the sun's death.
So in a very literal, physics-based sense, the event hasn't happened for us yet.
Exactly. It's not just that we don't know about it. In our local slice of reality, it hasn't occurred. Causality has not reached us. The information isn't here.
That is a blissful, terrifying ignorance. We are going about our day banking on a star that ceased to exist while we were making coffee.
And this brings us right to the conflict. The visual part is easy enough to grasp. Light takes time to travel, we get that. But the gravitational part, that is where physics broke down for about 200 years.
Right, because the sun does two main things for us. It lights up the room and it holds us in our chair. It keeps Earth in orbit.
It is the anchor, the center of the whole dance.
So here's the million-dollar question. The sun vanishes at time 0. We know the light stays for 8 minutes, but when does the gravity let go? When does Earth fly off into space?
Well, if you could travel back in time and ask Isaac Newton, he would give you a very confident, very clear answer. He would say, immediately.
Instantaneously.
Yes. Newton's law of universal gravitation, which he published in the Principia, treats gravity as a force that acts instantly across any distance. He called it action at a distance.
So in Newton's mind, there is an invisible kind of rigid tether connecting the sun and the Earth. If you cut the sun end, the Earth end goes slack at the exact same moment.
Precisely. Newton viewed the universe as a master clockwork mechanism. Space was just a stage, combiner. If you move a prop on stage left, the actors on stage right are instantly part of that new configuration. There's no lag.
Okay, so if Newton is running our simulation at time 0, the Earth just flies off its orbit. We career into deep space.
Right.
But we can still see the sun.
Correct. For 8 minutes, we would be flying wildly off course, drifting away from a star that is still sitting there, bright and yellow, in the center of the sky.
That feels deeply wrong. It's like the audio being out of sync with the video in a movie. It's just unsettling.
It felt wrong to Einstein, too. In the early 1900s, he was developing his theory of special relativity. And the core pillar of special relativity is the cosmic speed limit.
Nothing travels faster than light.
Nothing. Not matter, not radiation, and crucially not information.
And gravity is information. That's the key.
Think about it. Gravity tells the Earth where the sun is. It tells the Earth how to move, which way to curve. If the sun disappears and the Earth reacts instantly, that message of disappearance would have traveled 93 million miles in 0 seconds.
Infinite speed.
Which breaks the laws of physics. It would mean information traveled faster than light. And if that were possible, you could violate causality. You could effectively send messages back in time, create all sorts of paradoxes. Einstein just knew that Newton's instant action had to be wrong.
So he had a problem. He had the most successful theory in the history of science. Newton's gravity clashing with his brand new revolutionary theory of relativity.
And he spent 10 years trying to fix it, a whole decade. And the result was general relativity. He didn't just patch Newton's code, he rewrote the entire operating system of the universe.
This is where we get into the fabric stuff, space-time.
Yes. Einstein's huge leap was realizing that gravity isn't the force that reaches out and grabs things from a distance. Gravity is a curvature. It's the shape of reality itself.
We have to do the analogy, don't we? The rubber sheet.
We must. It is mandated by law in physics discussions. But let's critique it as we use it, because Hawking often pointed at its flaws, which is just as important.
Okay, lay it out for us.
Imagine a trampoline, or a large sheet of rubber stretched tight. That represents the fabric of space. Now, place a heavy bowling ball in the center.
That's a sun, it sinks down. It creates a dip or a valley in the sheet.
Right. Now take a marble, that's Earth, and roll it along the sheet. If you roll it just right, it won't go straight across. It will curve around the valley created by the bowling ball.
It orbits. It's trapped in the curve.
Now, here's the nuance. Is the bowling ball pulling the marble?
No. The marble is just following the shape of the rubber. It's following the path of least resistance.
Exactly. The marble is actually trying to move in a straight line, what physicists call a geodesic. But because the space it is traveling through is curved, that straight line looks like a circle to us in 3 dimensions.
So gravity is geometry. It's the shape of the road, not a rope pulling the car.
That is a beautiful way to put it. Gravity is the shape of the road. Now back to the magic gravity machine. We snatch the bowling ball away. The sun vanishes.
The dip in the rubber sheet has to snap back to flat.
Does it happen instantly?
No, of course not. If I poke a trampoline, the ripple takes a moment to travel to the edge.
Bingo. That snap, that restoration of flatness, travels as a wave, a gravitational wave. And Einstein, he did the math, he calculated the speed of that wave.
And let me guess, it's 186,000 miles per second.
It is exactly the speed of light. Gravity and light share the same cosmic speed limit. They travel in lockstep.
So the news that the sun is missing travels via gravitational wave at the exact same pace as the last photon of light from the sun's surface.
They are neck and neck. The darkness and the loss of orbit arrive together in the same package at the same time.
That resolves the paradox. We don't fly off while seeing the sun, we fly off exactly when the sun goes dark.
Causality is preserved. The universe makes sense again. But it leads to this profound and slightly spooky realization. For those 8 minutes, we are orbiting a dent in space that no longer has a cause. We are swinging around a phantom mass.
We are dancing with a ghost.
And we have no idea.
So here's the flaw in the analogy that Hawking mentioned. The rubber sheet is two-dimensional, right? It curves down into a third dimension that we can see from the outside.
Exactly. But our universe is three-dimensional space, so where does it curve?
Into a fourth dimension.
That's the problem. It's hard to visualize. But what's really being curved isn't just space, it's space-time, a four-dimensional fabric. The rubber sheet helps with the space part, but it completely leaves out the time part, which, as we'll see, is just as warped.
Okay, let's move the clock forward. We're counting down. 7 minutes. 7 minutes 30. People are finishing their lunch. The plants are soaking up those last ghostly photons. And then we hit the mark. 8 minutes and 20 seconds. T plus 8.
The arrival of the event. The light cone reaches us.
Describe that moment. What happens to the person on the beach?
It is simultaneous shock.
Yeah.
A 1-2 punch to our reality. First, the visual. The sky doesn't fade. It doesn't dim like a sunset. It snaps to black.
Instant darkness.
Absolute. Because the blue sky we see is just sunlight being scattered by the nitrogen molecules in our atmosphere. No sunlight, no scatter. The sky vanishes. The stars would appear instantly, blazing against the black void like diamonds on velvet.
And the moon. What about the moon?
The moon shines by reflected sunlight. Light takes about 1.3 seconds to get from the moon to us. So about 1.3 seconds after the Earth goes dark, the moon would just blink out.
That is just terrifying. A
Yeah.
sky with no sun and no moon, and at that exact same microsecond.
The floor drops out. Or rather, the retaining wall disappears. The gravitational curvature that was bending Earth's path into a circle suddenly flattens out.
So we stop turning. We just go straight.
We start turning. Newton's first law of motion takes over. An object in motion stays in motion in a straight line unless acted upon by an outside force. The force, or in this case the curvature, is gone. Earth flies off on a tangent into the dark.
We talked about Tyson's point on escape velocity. Usually leaving the solar system is hard work. It takes a lot of energy.
Very hard. To break free of the sun's gravity right now, we would need to increase Earth's current speed by roughly 40%. That's the escape velocity, about 1.4 times our orbital speed. It's a huge boost.
But in this scenario, we don't need to speed up at all.
No. The prison walls have simply evaporated. We're currently moving at about 67,000 miles per hour, or 30 kilometers a second, around the sun. When the gravity vanishes, we keep that speed, but instead of curving, we shoot straight out into the dark.
We become a rogue planet.
A drifter in the interstellar void. And Hawking brings up a fascinating point here about orbital chaos. He discusses how delicate and, frankly, how lucky our situation actually is.
How so?
He talks about the dimensions of space. In our three-dimensional universe, gravity follows what's called an inverse square law. If you double the distance from something, its gravity gets 4 times weaker. 2 squared is 4.
Okay.
That specific mathematical relationship is what allows for stable elliptical orbits. It's a perfect balance. If you nudge the Earth a little bit, its orbit will change slightly, but it will settle into a new, stable path. It corrects itself.
It's a forgiving system.
To a point, yes. But Hawking points out that if space had, say, 4 dimensions or 5, gravity would follow an inverse cube law or an inverse fourth power law. And in those universes, stable orbits wouldn't exist.
Oh, what happened?
Planets would either spiral into their sun or fly away into space at the slightest disturbance. There's no middle ground. The whole system would be unstable.
So we are balancing on a mathematical knife edge to begin with.
We are. And in our thought experiment, we've just kicked the whole balancing act over.
And it's not just us, right? It's the whole family. Mars, Jupiter, Saturn, they all go flying too.
It's this beautiful, terrifying unzipping of the solar system. And it happens in slow motion from our perspective.
Because of the light speed delay.
Right. Jupiter's about 43 light minutes away from the sun. So Earth goes dark and flies off at the 8-minute mark. But if you had a powerful telescope and looked at Jupiter,
You'd still see it orbiting the sun as if nothing had happened.
for another 35 minutes, yeah. Because the wave of gravity loss hasn't reached it yet. Jupiter is still held in orbit by the ghost of the sun's gravity. The ripple moves outward, releasing the planets one by one. Saturn at about 1 hour and 20 minutes, then Uranus, then Neptune hours later.
It's a cascading failure, a domino effect of darkness and chaos spreading through the system.
It creates this silent, orderly destruction. But for us on Earth, that's all irrelevant. We have much, much bigger problems.
Let's talk about the aftermath. We are flying in a straight line. The heater has been turned off. What happens to the biosphere?
Sagan paints a very vivid, very poetic picture here. He references the Voyager spacecraft.
The pale blue dot.
Yes, Voyager is out there, far beyond Pluto, sailing the sea of space. From its perspective, the sun is just a bright star. It offers no heat, no real comfort. It's just another point of light.
And now, Earth is Voyager.
Exactly. We are a lonely vessel in the cosmic ocean. The first thing we'd notice, besides the dark, is the radiation. Without the solar wind, the stream of particles from the sun pushing back against the interstellar medium, cosmic radiation would spike dramatically.
But the temperature is the real killer.
The temperature is the killer. The atmosphere acts as a pretty good blanket, so it holds heat reasonably well. It wouldn't be like a cartoon where everyone freezes into an ice block instantly.
So we'd have some time.
A little. We'd have a few days of residual warmth from the oceans and the ground. But then the exponential drop begins. Within a week, the global average temperature is below 0 Fahrenheit. Within a year, it's minus 100.
And the oceans, they're a massive heat reservoir.
They are. The surface would freeze over relatively quickly, forming a thick crust of ice. But ice is a fantastic insulator. The deep oceans, especially near hydrothermal vents, might remain liquid for thousands, maybe even millions of years, trapped under a shell of ice miles thick.
So life could continue down there.
Some life. The chemosynthetic bacteria, the tube worms, the weird fish that live near those vents, they don't care about the sun at all. They run on the Earth's internal heat, on chemicals from the planet's core.
They might not even notice.
They might not notice the sun is gone until the Earth's core eventually cools down billions of years later.
Yeah.
But for us, for the forests, for the animals,
We're done for.
it is the everlasting night, as Sagan put it. Photosynthesis stops immediately. The entire food chain collapses from the bottom up within weeks. And eventually it gets so cold that the atmosphere itself gives up.
What do you mean it gives up?
The air would freeze. Nitrogen and oxygen, the gases we breathe, they would turn into liquid and then into solid flakes. It would literally snow air.
It's no air.
The atmosphere would precipitate out, settling onto the frozen surface as a layer of frozen nitrogen and oxygen sludge. Earth becomes a naked frozen rock huddling through the void.
That is heavy. It really validates that quote Sagan used about the ancient hearth fire.
It does. In many ancient cultures, the hearth fire was the heart of the family, the center of life. If the fire went out, the family was considered dead. The sun is the ultimate hearth. When it dies, the family of Earth dies with it.
It makes you appreciate that giant fusion reactor in the sky a little more.
Ideally, yes. It's easy to take for granted.
Okay, I want to pivot. This is fascinating. We've talked about the space part, the Earth flying off. We've talked about the gravity part. But we've danced around a core concept that links them all. Einstein didn't just link space and gravity. He linked space and time.
Space-time. You cannot pull on one thread without moving the other. They are a single, unified thing.
So in this deep dive into time, I have to ask, if the sun vanishes and gravity changes, does time change for us?
This is where we get into the really mind-bending, almost philosophical implications of general relativity. And the answer is yes, absolutely.
Explain that. How does gravity affect time?
Gravity warps time. This is a real phenomenon known as gravitational time dilation. The rule is simple. The stronger the gravity, the slower time moves.
So right now, on the surface of the sun, time is moving slower than it is here on Earth.
Correct. And here on Earth, time is moving slower than it is in deep space, far away from any mass. Time flows at different rates all over the universe. There is no single master clock.
Is this just a theoretical math thing? Or is it real? Have we measured this?
Oh, it is 100% real and measurable. We first confirmed it with the Scout D rocket in 1976. They put an incredibly precise atomic clock on the rocket and shot it straight up, away from Earth's gravity to an altitude of about 6,000 miles.
Yeah.
The clock on the rocket ran faster than the identical clock they left on the ground. Not by much, but by exactly the amount Einstein's equations predicted. Gravity was literally dragging on the flow of time down here.
That is wild.
It's practical, too. It's why your GPS works. The satellites that make GPS possible are orbiting about 12,000 miles up.
So gravity's weaker up there.
Much weaker.
Yeah.
And their clocks run faster by about 38 microseconds every single day compared to us down here on the surface.
38 microseconds doesn't sound like much.
In the world of light speed calculations, 38 microseconds is an eternity. If the engineers didn't program the satellites to artificially slow their clocks down to match ours, to correct for this relativistic effect, your GPS accuracy would drift by miles every single day.
So I'd miss my turn by a whole city.
You would. We are literally correcting for the curvature of space-time in our cars every day.
Unbelievable. Now bring this back to the magic gravity machine.
Okay. The sun vanishes. The massive bowling ball is gone from the rubber sheet.
So the curvature of space-time in our region flattens out.
And so the drag on time in the solar system is released.
So time for us would speed up.
Theoretically, yes. As the gravitational wave passes us, not only does space flatten, allowing us to travel in a straight line, but the flow of time slightly accelerates to match the flat rate of the universe. It's a tiny, tiny effect for something like the sun, but it's real.
Sagan used a great analogy to explain these relativistic effects. The scooter.
Ugh. The Einstein scooter. This was one of his favorite ways to explain special relativity, the effects of speed. But it ties into the same fundamental geometry.
He said to imagine you are riding a scooter, but the speed of light isn't 186,000 miles per second. Imagine the speed of light is slow, like 25 miles per hour.
Right. So you can easily reach the speed of light on your moped.
Yeah.
As you accelerate, the world starts to behave according to Einstein's rules, but in a way you can actually see.
He described the visual distortion first. The world gets weird.
Yeah. As you approach the speed of light, things ahead of you get compressed. The buildings would look squashed. The light would shift to blue. That's blue shift, because you're smashing into the light waves, compressing them.
And behind you?
Red shift. The waves get stretched out as you move away. The world behind you looks red and distant. At the time. That's the real kicker.
If I'm zooming past you on my scooter at 99% of the speed of light,
Yeah.
what do you see?
If I look at your watch as you zoom by, it would look like it's almost stopped. Your time is moving incredibly slowly relative to mine. You are nearly frozen in time.
And from my perspective on the scooter, what do I see when I look at you?
You see the rest of the world aging rapidly. You might take a 10-minute ride around the block, but when you stop and get off, you find that years or even centuries have passed for everyone else.
The classic Planet of the Apes scenario.
Or Interstellar. The point is, you cannot separate motion through space from motion through time. They are two sides of the same coin. The faster you move through space, the slower you move through time.
And that's why the 8-minute gap exists for the sun.
Exactly. The delay isn't a bug in the system. It's a fundamental feature of the geometry. The distance to the sun is the time it takes to communicate with it. You can't separate them.
Okay, so we've frozen the Earth, turned it into a rogue planet, and messed with the flow of time. I want to zoom out a bit. Why does this thought experiment matter? Why should the listener care about a scenario that is hopefully impossible?
It matters because it reveals the invisible structures that keep us safe every single second of every day. Tyson talks about the cosmic dance. We tend to view gravity as a cage. It keeps us stuck to the Earth, stuck in orbit.
Yeah.
But it's also a shield.
A shield? How so?
Look at Jupiter. Tyson highlights this all the time. Jupiter is the vacuum cleaner, the big bouncer of the solar system.
Because it's so big.
It has a massive gravitational field. It attracts comets and asteroids that come screaming into the solar system from the outer dark. It either swallows them whole or, more often, uses its gravity to slingshot them out into deep space, away from us.
So it acts like a goalie for the inner planet.
A cosmic goalie, exactly. If Jupiter weren't there, or if its orbit wasn't stable and predictable, many, many more of those rocks would head for the inner solar system. They'd head for Earth.
So without the sun holding Jupiter in its stable orbit.
The goalie leaves the net. The entire structure of our safety dissolves. We rely on the precise gravitational balance of the whole system to avoid being constantly bombarded by extinction-level events.
It really highlights that we are in a Goldilocks scenario, not just for temperature and water, but for gravity, too.
We are balanced on a pinhead in so many ways. The whole thing is incredibly fragile.
I also love the human side of this story. The fact that we, these tiny mammals on a small rock, actually figured this out. It's just staggering.
The history of the science is incredible. Sagan tells the story of Einstein as a teenager in Italy.
The famous dropout.
Yes, he dropped out of the rigid German school system because he found it stifling. He was wandering the roads of Pavia, just thinking, imagining. His teachers had told him he would never amount to anything.
Why? What was his problem in school?
He asked questions that disrupted the discipline of the class. He refused to just memorize Newton's equations. He wanted to understand the mechanism. He famously imagined chasing a beam of light. If I catch up to it, what does it look like?
And that daydream led to relativity.
It did. It took a long-haired teenage dropout, as Sagan put it, to overthrow the 200-year reign of Isaac Newton.
And we verified it. It wasn't just chalkboard math. We proved it.
The 1919 eclipse, this is a pivotal moment in human history. A British expedition led by the astronomer Arthur Eddington went to the coast of Africa. They waited for a total solar eclipse.
Why an eclipse specifically?
You need the sun's bright disk to be blocked out so you can see the faint stars right next to it in the sky. Einstein had predicted that the sun's immense gravity would actually bend the light from those distant stars as it passed by.
Like a lens, a gravitational lens.
Exactly. Newton's physics said light has no mass, so gravity shouldn't affect it. Light should travel in perfectly straight lines. Einstein said no, light follows the curve of space. If Einstein was right, the stars would appear to be shifted slightly from their true positions in the sky.
What happened?
They took the photographic plates, they waited months to get back to England and measure them carefully against comparison plates. The stars had shifted, and the amount they shifted was exactly what Einstein's equations predicted. The universe was curved.
I can't imagine the feeling of seeing that data for the first time. Realizing that the fundamental nature of reality is not what we thought it was just yesterday.
It is the ultimate aha moment. It confirmed that we live in a universe governed by space-time, not just space and time as separate things. It made Einstein a global superstar overnight.
Okay, before we wrap up, I want to go back to the magic gravity machine one last time.
All right, let's fire it up again.
We used it to destroy the sun. But the sources, particularly Hawking, hint at something even wilder. If gravity curves space-time, and if we could control gravity, really control it, could we curve time into a loop?
Ah, the time travel question. It always comes back to time travel.
Could we go back and stop the sun from vanishing in the first place?
Well, here's the thing that bothers a lot of physicists. The equations of general relativity do not strictly forbid time travel. There are solutions to the math that allow for what are called closed time-like curves.
A loop. You walk forward in time and end up in your own past.
Theoretically, yes. If you had a region of space-time that was curved enough, say by an infinitely long spinning cylinder or a wormhole, a bridge between 2 points in space-time, the math says it could work.
Hawking was skeptical, though, right? He didn't think it was possible.
He was a realist. He came up with something he called the chronology protection conjecture.
Which is a fancy way of saying, what?
The universe won't let you do it. Hawking argued that as soon as you try to build a time machine, say by opening a wormhole and trying to stabilize it, quantum mechanics would step in. Vacuum fluctuations and radiation would pour into the wormhole, loop through time, and amplify instantly, creating an infinite feedback loop of energy that would destroy the machine.
Feedback, like a microphone getting too close to a speaker and creating that horrible squeal.
Exactly. A feedback loop of energy that blows up the bridge before you can cross it. He believed the laws of physics conspire to keep the world safe for historians.
He also threw that party, right? The famous party.
The Time Traveler's Party. A brilliant experiment. He held a reception with champagne and balloons and everything, but he didn't send out the invitations until after the party was over.
And no one came.
No one came, which he took as pretty solid experimental evidence that time travel from the future is not happening.
Or maybe time travelers just have better things to do in the future than hang out at a physics party.
Perhaps. Or maybe they are observing the Prime Directive and just watching us from an invisible cloak. Who knows?
So we probably can't go back. We are stuck riding the arrow of time forward.
1 second per second. That is our speed. No more, no less.
Well, let's hope the sun sticks around then.
I think we're good. It has about 5 billion years of hydrogen fuel left in the tank.
That's comforting. So what is the big takeaway here? We've covered a lot of heavy, mind-bending physics.
For me, it is about connection and perspective. The next time you walk outside and feel the warmth of the sun on your face, don't just take it for granted. Remember the journey that energy took to get to you.
The 8-minute commute across 93 million miles of nothing.
Right. Realize that you are physically connecting with the past. You are touching a ghost of an event, a fusion reaction that happened 8 minutes ago.
And you are trusting a gravitational tether you can't see or feel.
And you are relying on the curvature of a four-dimensional fabric to keep you from flying off into an intergalactic void at 67,000 miles per hour. Gravity isn't just a rule in a textbook.
Yeah.
It is the geometry of our home. It's the invisible hand holding us safe.
I love that. The tether isn't a rope, it's the shape of the road.
Exactly.
So here's my challenge to you, the listener. The next time you see a sunrise, or a sunset, safely, of course, take a second to acknowledge the gap. Acknowledge that you are looking at a delayed broadcast, and remember that in that gap, that 8-minute window, lies the secret structure of the entire universe.
And if it suddenly goes dark, well, at least you know you have exactly 8 minutes to finish your drink.
Dark. I like it. Thanks for taking this dive into the void with us.
A pleasure, as always.
Keep looking up. We'll see you on the next Deep